Have you ever wondered why we need a red-black tree when standard binary search trees already exist? In an ideal world, a binary search tree has a balanced height, offering extremely fast logarithmic search times. But if we insert data in sorted order, the BSD degenerates into a single long chain. This turns our fast tree into a slow linked list, where search time degrades to linear time. To prevent this degradation, we need a self-balancing tree that automatically keeps its height short. A red-black tree achieves this balance by coloring each node either red or black and enforcing 5 rules. These properties guarantee that the tree remains balanced, keeping worst-case search times at logarithmic speed. Let's explore these 5 core properties one by one to see how this magic happens. The first property of a red-black tree is simple. Every node is colored either red or black. Each node contains a color field, storing a single bit to represent this color state. This coloring is the foundation that allows the tree to balance itself during insertions and deletions. The second property states that the root of the tree is always black. This rule simplifies balancing and prevents unnecessary recoloring at the very top of our tree. Even if an operation attempts to turn the root red, we always recolor it black. With the first 2 properties established, we ensure color consistency starting right from the top. Now let's look at the third and fourth properties, which regulate leaves and adjacent nodes. The third property states that every leaf, represented by sentinel nil nodes, must be black. These nil leaves do not store keys. They act as terminal markers for every empty branch. By treating every empty child as a black leaf, we create a uniform boundary around the tree. The fourth property prevents consecutive red nodes. If a node is red, both children must be black. This means that we can never have 2 red nodes adjacent to each other along any path. However, black nodes can be adjacent to other black nodes without any restrictions. This property restricts how tall a branch can grow, because red nodes must alternate with black nodes. Next, we will see the fifth and most critical property that mathematically guarantees perfect balance. The fifth property is the black height property. All simple paths to descendant leaves have equal black nodes. Let's count the black nodes along each path from the root to the nil leaves. Notice that every single path contains exactly the same number of black nodes. Combined with the rule of no adjacent red nodes, this property has a remarkable mathematical consequence. The longest path can never be more than twice the length of the shortest path. This strict relationship guarantees that the height of the tree remains bounded by O log n. In summary, these 5 simple rules keep the tree self-balanced and highly efficient for all operations. Now you understand the magic behind red-black trees and why they are used in systems everywhere. Let's explore the insertion algorithm for a red-black tree, which maintains perfect balance after adding new elements. We start with a standard binary search tree insertion to find the correct leaf spot. Crucially, we always paint this newly inserted node red. Why do we color it red? Because introducing a red node preserves the critical black height property across all paths, ensuring property 5 is not immediately violated. If we inserted a black node instead, we would instantly disrupt the black height balance, which is incredibly complex to restore. However, inserting a red node introduces another risk, violating property 4, the double red rule. If the parent of our new node is also red, we have an active conflict. We must now resolve this violation, using the uncle node as our essential guide to determine our next balancing steps. When the parent of our newly inserted red node is also red, we must inspect the sibling of the parent, which is the uncle node. Case 1 occurs when this uncle node is red. Since both the parent and the uncle are red, we know the grandparent must be black to maintain initial validity. To resolve this double red violation, we perform a simple recoloring. We paint both the parent and the uncle black, and we change the grandparent from black to red. This elegant recoloring resolves the local double red conflict while perfectly preserving the black height of all, because we pushed the black color down. However, since the grandparent is now red, it might conflict with its own parent. Therefore, we move our active pointer up to the grandparent and recursively repeat our balancing process. But what happens if the uncle node is black? This brings us to cases 2 and 3, where simple recoloring is no longer sufficient, and we must perform tree rotations to restore balance. Case 2 represents the triangle configuration, where the new node, its parent, and its grandparent form a zigzag shape. For instance, the parent is a left child, but the new node is a right child of that parent. To simplify this arrangement, we perform a left rotation on the parent node. This rotation transforms the triangle configuration into a straight-line shape, which is case 3. Crucially, this rotation is a local structural change that perfectly preserves the binary search tree ordering. We then update our active node pointer to the former parent, which has now become the child, and proceed directly to case 3. Case 3 represents the line configuration, where the new node, its parent, and its grandparent form a straight line. For example, the parent is a left child, and our active node is also a left child. To resolve this final case and restore proper balance, we perform a rotation on the grandparent node. Specifically, we execute a right rotation on the grandparent. Following this rotation, we swap the colors of the parent and the grandparent. The parent becomes black, and the grandparent becomes red. Because the parent is now a black root of this, and both its children are red, the double red violation is completely eliminated, while the black height remains perfectly balanced. The tree is now a fully valid red-black tree, and the insertion algorithm terminates. With these 3 elegant cases, insertion is guaranteed to complete in logarithmic time. Now, let's look at the algorithm to delete a node from a red-black tree, starting with standard binary search tree deletion. If the node has 2 children, we replace its value with its in-order successor and delete that successor node instead. This reduces our problem to deleting a node with at most 1 child. Now, we examine the color of the deleted node. If the deleted node was red, we can simply remove it and replace it with its child. No rules are broken. However, if the deleted node was black, its removal reduces the black height of its by 1. To track this missing black node, we conceptually assign an extra unit of blackness to its replacement node, turning it into a double black node. This double black violation represents a deficit of black height that we must resolve to restore the structural balance of the red-black tree. To resolve a double black node, we inspect its sibling and the sibling's children. Let's look at case 1, when the sibling is red. Since the sibling is red, we perform a left rotation at the parent and swap the colors of the parent and sibling. This pushes the red sibling up and assigns a new black sibling to our double black node, transforming the situation into case 2, 3, or 4. Next is case 2, when the sibling is black and both of its children are black. In this case, we can pull 1 unit of blackness out of both the double black node and its sibling, passing it up to their parent. The sibling becomes red, and the double black node becomes a single black node. If the parent was red, it becomes black, completely resolving the deficit. If the parent was already black, it now becomes the new double black node, and we repeat our analysis up the tree. Now let's examine case 3 and case 4, which occur when the sibling is black, but at least one of its children is red. In case 3, the sibling's child that is closer to our double black node is red, while the far child is black. To fix this, we perform a right rotation at the sibling and swap the colors of the sibling and its red child. This turns the near red child into the new sibling, which is now black, and pushes the far child to be red, successfully converting the structure into case 4. In case 4, the sibling's far child is red. We perform a left rotation at the parent and recolor the nodes so that the sibling takes the parent's original color, the parent becomes black, and the far red child also becomes black. This rotation and recoloring fully absorbs the extra unit of blackness. The double black node becomes a standard black node, and the balance is perfectly restored. Let us trace a complete deletion example to see all these rules in action. We start with a perfectly balanced red-black tree containing keys 13, 8, 17, 11, and 15. Suppose we delete the black leaf node with key 8. Since 8 is black and has no children, its replacement is a double black null leaf. We look at its sibling, 17, which is red. This matches case 1. We perform a left rotation at the parent 13 and swap their colors. Now our double black null leaf has a black sibling, 15, with no children. This matches case 2. We pull the blackness up. 15 becomes red, the double black null leaf becomes a single black null, and the parent 13, which was red, becomes black. The double black deficit is fully absorbed, and our red-black tree is beautifully balanced once again.